Yeah, I'm going to cover the notes from section 2.1, multiplication and division of rational expressions. So a couple definitional things. A rational expression sounds complicated, but a rational expression is really an expression that involves fractions. The word rational contains the word ratio, and ratio means fractions. And then we're first going to talk about when are they undefined. Undefined means that there's no possible solution where the solution does not exist. Okay, and so um, we're only going to spend a few minutes on this. It's a simple idea. Um, I think if I explain it, maybe using this calculator, let me turn on a light. Hopefully this calculator will start up. Okay, so you should be able to see that. And so if I take a number and I divide it by, I'll just take 1 and divide it by 0.001. So I'm dividing it by a very small number. Okay. You can see my answer is very large. It's 1,000. If I take that 1 and divide it by even a smaller number, 0.000001, the answer, let me do it again. 1 divided by 0.00001, you can see now it's 100,000. I'll do one more, but just to show you, as the number that I divide by gets smaller, the answer gets bigger. Point zero. So if I divide by that, you can see that I think it's 10 billion, right? So imagine the numbers that I divide by get smaller and smaller and smaller and smaller. The answer gets bigger and bigger and bigger and bigger. Well, as it approaches zero, it gets huge, but it could never hit zero because the answer would be infinity. So the where a rational expression is undefined is any value that makes the denominator equal to zero. Because see what happens if I take 1 and I divide it by, instead of a really, really small number, I try to divide it by 0, it throws an error. Okay, it does not exist. The answer is actually infinitely large. Okay, and there's no such number as infinity. So we have to protect against the possibility of, in any math problem, dividing by a 0. Okay, if it's in a computer, the computer will crash. It cannot handle division by 0 because it does not exist. Okay, so what we do is very, very simple. If the question is find the values that make the expression undefined, okay, in this case, all we're worried about is what values create a 0 in a denominator. Well, all you have to do is set the denominator equal to 0 and solve it. Okay, so you can see in this first example, it's just a linear equation, right? If I set this equal to 0 and solve it, what would I do? Subtract 35 and divide by 7, right? And so that would be the value that must be excluded from any solutions. So um, here I did it by factoring, but I didn't really need to. Either way, you're going to get -5. Okay. In the factoring mode because we're going to be doing a lot of factoring. So this expression can accept any value for x except a -5 because it would create a 0 in a denominator. Well, you can see here on this next example that these two things are factored, right? And we have already talked about solving quadratic equations by factoring, set it equal to 0, and then set each factor equal to 0. So if it's factored, then we take each factor, set it equal to 0, and solve it. So here there'd be two answers that cannot be allowed as values for x. You cannot ever give it a -6 or a -2. And if you put -6 in here, that becomes 0 because it's -6 plus 6. 0 times anything is 0. That creates a 0 in the denominator. Likewise with the -2. So where, I've talked about the importance of being able to factor. We'll take a look at this particular expression, and you can see that the denominator is quadratic, right? And we're looking for values that make this equal to 0. So what would we do? We would set it equal to 0 and solve it. Well, being quadratic, what we have learned is to factor it. I'm not going to go through all the factoring. I'm just going to show you the factorization. Hopefully you can see how that came about. So once I factor it and set it equal to zero, that means each of these factors gets set equal to zero to find values that would make the denominator zero. So if I put a 10 or an 8 into this expression, either one of those is going to produce an answer of zero, which cannot be because you cannot have a zero in the denominator. Okay, so I'm only spending 5 minutes on this because there's not much else to say, but you do have to understand when they ask you what values makes the expression undefined, just set the denominator equal to zero and solve. Next, we're going to take a look at simplifying rational expressions. And simplification is very, very important. We do not want to have any undue complexity in expressions. And in class, I'll explain in detail why, but for the sake of keeping the video short, I won't. But when you simplify a rational expression, what you want to do, and here are the steps, but you can see that you factor both the numerator and denominator, you cancel out common factors and simplify the results. So let's take a look at an example that would be obvious. Now here's two numbers being multiplied on top, two numbers being multiplied on the bottom. They are factors, right, because they are being multiplied. And if I factored out 9 to be 3 times 3, and I factored 12 into 4 times 3 and 15 into 3 times 5, you can see that I have all these numbers on top multiplying these numbers on bottom. If they're all being multiplied and divided, I can cancel common factors, right? I can divide both of these by themselves, 4s. These are really 1s. Anything over itself is a 1, so these cancel out to 1s. This 3 can cancel with that 3. And so the only thing left on top after cancellations are 1s. And on the bottom, the only number that didn't cancel, the only factor that remained is 5. Okay, so the simplification process is we're not going to be doing just numbers, but you factor the numerator and denominator so that everything's being multiplied. And then all those common factors cancel out, and the result is a simplified expression. So here's an example of already factored expression, right? And so some have numbers, here's some binomials, and as long as what's inside the parentheses is exactly the same, then they are exactly the same thing because x is the variable. So whatever value of x, it's going to be the same in the expression. So that means these have to be identical, for example. So likewise, I can just cancel common factors, right? Those cancel the 1. The 2 doesn't have anything to cancel with. X minus 1 can cancel with that. And again, every time you cancel a common factor, it's really just 1, anything over itself. So what's left on top? Only 1s. What's left on the bottom? I've got a 2 and an x plus 3. And so this is the simplification of something that was much more complicated. Okay. One thing to be careful of is do not, if you have an expression like this, you cannot cancel these x's and you cannot, do something like that. Why? Because these are not factors. They're part of an addition. Okay. You cannot mathematically, this doesn't work. So for example, if I had 3 plus 9 and I have it over 3 plus 3, if I just do the math, I end up with 12 over 6, which is equal to 2. But if I looked at it as, well, I can cancel these 3s, these can be 1s, and 3, what am I going to end up with? 3 plus 1, I'm going to have 4 over 1. Well, we know that's not the answer. The answer to this is 2. This is not mathematically permissible. It has to be factors, things that are being multiplied to cancel. Okay? So when we take a look at some of these examples, and this is where the factoring, I told you and warned you that it's going to come right into play. So here we have an expression. Okay, the first step, these are not all factors. You got addition, subtraction in there. You got to factor the expression completely, both the numerator and denominator. And if I do that, then on top, I take out the greatest common factor. I factor this trinomial, I get this. Again, I'm not going to explain the factoring. But when it's fully factored, I do have this expression, the x minus 1 is common in the numerator and denominator. So they cancel each other out to be 1s. The 9 and the x plus 5 do not cancel. So the simplified expression, you can see this is much easier, much simpler. to work with is this. Okay. Likewise, again, factoring, these are trinomials. I cannot cancel these x squareds. Again, why? Because you have addition involved. Everything has to be multiplied. So if I factor the top and the bottom, here's the factorization. The common factors in the numerator and denominator are the x plus 4. If I cancel that out, what's left is the x plus 10 and the x plus 7. Okay, it's pretty basic, but it's completely dependent on you being able to factor. Now we're going to look at the idea of opposites. Okay, opposites in rational expressions. What makes something an opposite is all the numbers and variables are there, but the signs are all completely backwards from each other. Okay, and so what that means, so for example, let's say I had x plus 3 on top and minus 3 minus x on the bottom. And I go, okay, can I factor, can I cancel these? Well, these are not exactly the same. The signs are wrong. And so an opposite means that I can factor out a negative 1. And when I factor out a negative 1, what does that do? It flips every sign on the inside. And so that minus 3 becomes a plus 3, and it doesn't matter what order I write them in as long as the signs, and the minus x becomes a plus x. And so now I do have identical binomials that can then be factored, but what gets left over is a negative 1. Okay, so when you have a situation where you recognize that you have opposites, everything is the same except the signs are backwards, you can cancel those terms, but replace it with a negative 1. You've effectively canceled out a negative 1. So let's take a look at the notes. So here, just like the example I gave, on the bottom I got x plus 14, but on top I have minus 14 minus x. I got the right numbers, right variables, but the signs are completely backwards. Okay, so what can I do? I can effectively cancel or remove a negative 1 factor out of the top. What does it do? It flips all the signs on the inside. Now these are identical. They can be canceled, but what was left is that negative 1. Okay. Likewise, over here, I got 6 minus x, and on the bottom, if I factor this by binomial difference of squares, I end up with x plus 6, x minus 6 on the bottom, but on the top, I originally had x minus 6, which is backwards from what I need to be able to cancel. So what do? I'll factor out a negative 1. I'll put the negative sign in front, and I'll flip the signs of the numerator. I factored out a negative 1 out of that numerator. Now the x plus 6's can cancel, and what's left, the negative in front, this canceled to a 1, so the only thing left on top when you cancel would be a 1, and then the x minus 6. Okay? So again, factoring. So if I fully factor the top, you can see that I'm going to end up with a situation where I have an opposite. Okay? Because on the bottom I have 2 minus y, and on top I have y plus 2, but I can remove a negative sign, and I can rewrite the term where the signs flip. Now they match. Now they can be canceled. But don't forget that you put that negative sign in front, you factored out a negative 1, and there would be your answer. Okay, so you're going to see lots of opposites. They're real easy. Just cancel, but make sure that you put a negative sign in front or change the sign in front. Now we're going to look at multiplying rational expressions. Again, we're multiplying fractions, basically. So as long as you understand that you really should know how to do this already mathematically, the only thing that makes it more complicated is the fact that you got to do some factoring. Okay, so let's take a look. So you're going to factor everything, all numerator and denominators completely to simplify the expression. And then when we multiply fractions, the rule when you multiply two fractions is you just multiply the numerators and you multiply the denominators. Well, notice these are all factors. So any common factors can be canceled to simplify it. So for example, using just numbers, if I had 14 over 22 and 11 over 21, well, if I factor the numerator and denominator, into 7 times 2 times 11 and 2 times 11 times 7 times 3, all the factors, then I can one for one cancel any common factor on the top and the bottom, the numerator and denominator. So the 7's cancel, the 2's cancel, the 11's cancel. Everything canceled on top, that leaves a 1. The only thing left in the denominator is the 3. So this would reduce to 1/3. Okay, so the only difference in the types of problems you're going to be doing in this section is you have to factor to turn things that are not multiplied, the x plus 3 and you have the plus sign here, turn these into multiplication by factoring and then cancel common factors. So if I factored everything, well, the x plus 3 and the x plus 7 don't factor, but I can take out a 4 and multiply that by x plus 7. So you can see I have three things on the top multiplying each other. Those are factors. On the bottom, I can't factor x plus 7 any further, but I can take a 9 out of this. Gives me x plus 3. Here's 3 factors on the bottom. Anywhere that they're common, I can cancel. These x plus 7s can cancel each other. The x plus 3s can cancel each other. You can see the only thing left is going to be the 4/9. Okay. So these can get a little bit complicated in terms of looking ugly, but the key is factoring, right? If you can factor, these are really pretty simple. So you look here, I've got this ugly looking multiplication problem of fractions, but every single element of the fractions can be factored. So what do? I factor everything on top, everything on the bottom. And when I do that, again, this looks like a mess. I've already done the cancellations, but here's the full factorization of the top. Here's the full factorization of the bottom. And then I go, okay, what factors are common? Well, the x plus 10s can cancel, and x plus 2 can cancel, or excuse me, and x minus 2 can cancel here. The x plus 3s can cancel here. And that's it. The only thing left over is an x minus 3 that didn't have a matching on the bottom, and an x plus 2 that didn't have a matching factor on top. So the solution would be x minus 3, x plus 2. Being able to factor makes these really relatively simple. Factor everything, cancel common factors. The last thing we'll look at is dividing rational expressions. Okay, so again, dividing fractions. We know how to do that already. We know that if we have two fractions that are dividing each other, we turn it into a multiplication problem, and we take the reciprocal of the divisor, the second fraction. So instead of multiplying by c over d, we flip it to d over c. And then it's a multiplication problem. We just did it. So there's only that one additional step involved, right? So your eyes, initially have to focus in on the fact that this is a division problem involving fractions. Okay, so probably the best thing to do is to go ahead and rewrite the problem with the second fraction flipped and then factor everything. So x squared minus 9 factors to x minus 3x plus 3. The x minus 7 came up on top because we did reverse this. We did take the reciprocal. So the x plus 7 is on top. On the bottom, we factored x squared plus 4x minus 21 to this. And then what was on top, the 5x, is now in the denominator. Okay, and then we look for everything. Everything's being multiplied. Everything's a factor. So x minus 3's cancel each other. X plus 7's cancel each other. There's an x plus 3 that cannot find anything to cancel with, and there's a 5x that has nothing to cancel with. So the final answer would be x plus 3 over 5x. One other example, well, this is clearly a fraction. 15u doesn't look like a fraction, but it is, because any whole number can be written as a fraction over 1. Since it's division, what do we have to do? We have to take the 15 over 1 and flip it, which makes it become 1 over 15. So the reciprocal would be 1 over 15u. And then we do the same thing. We multiply. We have 5 times u, and when the one that's in the denominator comes up, there it is right there. And on the bottom we have 7, and then the 15u goes to the bottom because we did the reciprocal to multiply it. And if you kind of factor 15, you can get 5 times 3 times u. And so here's all the factors. Fives cancel. I've got a u that cancels. I've got a U that can't find another one that can't. Again, once you cancel it, you can't cancel it again. So this U cannot find another U. One you don't worry about. And then you have the 7 that has no matching factor and a 3 with no matching factor. So what's left on top is a U. On the bottom, the 7 times 3 is 21. There would be the simplification. Okay. This last one is a challenge question. I'm not going to go through it. It's just it looks horrible, but it's division. So what are you going to do? You're going to flip this one around to turn it into multiplication, factor everything, and then cancel all the common factors. And if you do that, I'll leave it as an exercise, but it's going to simplify to z plus 4 over z plus 2. Okay? So that's the first section of Unit 2.